who is Francesca is a very old friend and a former colleague at Imperial College in London. She joined Imperial, if I remember well, in 1991, right? And doing her PhD with Bob Kowalski. And she has never left since, essentially, right?
Essentially, yes.
Right. And she has been for a long time one of the most prominent members of the international logic and computation community. At the moment, she's professor in computational logic and Royal Academy of Engineering JP Morgan Research Chair on argumentation-based interactive explainable AI, still at the Department of Computing. She's the founder and leader of the Clark Computational Logic and Argumentation Research Group and of the Faculty of Engineering Explainable AI Research Center. Her research interests lie within the broad area of knowledge representation and reasoning in AI, explainable AI, and in particular include argumentation, argument mining, logic-based multi-agent systems, non-monotonic default diffeasible reasoning, machine learning. I think after this long list of titles, I can leave the floor to Francesca for her talk. Please, Francesca, welcome.
Thanks a lot. Thanks, Marcello, for the invitation, and Paolo for arranging the seminar. It's a great honor to be here. And also, as I said, I'm looking forward to hearing your thoughts on this technical talk that I'm unusually giving these days. The talk is on argument graphs and assumption-based argumentation. Assumption-based argumentation is the form of structured argumentation I've mostly worked on for donkey's years, but the use of argument graphs in connection with it is rather novel, and I believe is a notion that can benefit other forms of structured argumentations and maybe other forms of logical reasoning. The work is with Rob Craven, who was the postdoc on the project in which this work was developed. I'm going to talk to you about, the motivation for this work, give you some essential background on assumption-based argumentation, and then provide the formal definitions and intuitions behind this new form of structured argumentation, which called graph-based ABA. So the main reference for this work is a 2016 AI journal paper with Rob. So let's start with some high-level motivation. So structured argumentation often uses forms of trees to represent argument as deductions, fundamentally. ABA, assumption-based argumentation, is one such forms of structured argumentation, but ASPIC, I believe, also uses trees to represent arguments. So this conception of arguments as tree-shaped deductions is there to enforce a form of relevance in argument of the support of arguments towards the claim. But this practice actually has undesirable effects. In particular, it may introduce circularity and redundancies in arguments and in sets of arguments. And this is even so when the trees are required to be finite, as is the case in ABA, of course. So the main motivation for this work is to avoid these undesirable patterns without imposing, if you like, post hoc, some constraints on the arguments and sets of arguments so that these undesirable patterns are avoided. So what we do is opt for a different conceptualizations of arguments and of sets of arguments as graphs, and this allows us to organically avoid these undesirable patterns. So this is the overall, if you like, view of this technical work. Let's start now with some essential background and preliminaries before I can tell you how we achieve this. So ABA is a form of structured argumentation. In a nutshell, it boils down to envisaging frameworks which are tuples of 4 elements. The first 2 are basically a deductive system in whichever logic you want them to be. As soon as we have a compactness result for the deductive system, we're fine. So you have a set of sentences, that's your language, and some inference rules, which are of the form conclusion S0 here, if premises S1, Sm here, and all the SIs are elements of your language. So that's your starting point, the deductive system. What ABA then does is it singles out some of the sentences in the language as the assumptions, and these are basically the things you can use to build arguments, but that you can object against. And the objections are via arguments for the contrary of these assumptions. So contrary is the last element of these tuples, and they are basically total mapping from the set of assumptions to the language itself. So each assumption comes with a contrary. That contrary is the mechanism, the handle we use to argue against the assumptions. And by arguing against the assumptions, we argue against the arguments that are built from those assumptions. So within the specific setting of this talk, and in other work we're doing as well, we are focusing on what we call flat ABA frameworks, which basically can be seen as restricted types of ABA frameworks where the rules are such that no assumption can occur in the conclusion of these inference rules. So this is a restriction, and ABA is more general than that, but in this talk I will focus on these restricted types of ABA frameworks. So these are, as a standard in structured argumentation, you are given the building blocks of arguments and attacks between arguments, and then you use these building blocks to define the arguments and the attacks between the arguments. And in ABA specifically, we define arguments as proofs. This should all be very kind of familiar to you. And proofs are finite trees. The nodes of the trees are labeled with sentences in the language L, plus we use a specific sentence true that is not part of the language to accommodate the fact that some of the inference rules may have an empty body. And the root of this tree is the sentence for which we're building a proof. We have a bunch of conditions we impose that use the inference rules. I'm not going to give them to you now, but I'll give you examples later. And then we say that the set of sentences in the language that label the leads are the support for these proofs, okay? Now, arguments are specific proofs which are supported by assumptions only. Okay, so such that the leaves are all labeled by assumptions. And then we can say that an argument attacks another argument if the first argument proves a sentence whose contrary is in the support of the second argument. Okay, I pause 1 second, and I didn't say at the beginning, but if there are questions, please ask them as they come along. Don't wait. But I don't see your questions, so I don't know, Paolo, Ada, or Marcello, Ada, you tell me or you shout.
I have to. Okay, I will tell you if there are questions.
Okay.
No questions so far. Okay.
Okay, good. So basically, arguments are defined as proofs in this deductive system, and also we define attack based on arguments proving the contrary assumptions in support of other arguments. So this is a very simple definition. Then we define extensions, which are basically semantics for these argumentation frameworks, as sets of arguments that satisfy some conditions, which are defined in terms of attacks. Again, I'm not giving you the definition. This is really essential background. But a simple example of what an extension may be required to satisfy is that it is not conflict-free, that it is conflict-free, namely that no argument within the set attacks any argument within the set. So this is a basic semantic requirement which is at the heart of argumentation. Argumentation is all about resolving conflicts and dealing with possible inconsistencies. And this basic requirement is what all semantics impose. But there are other requirements that are being asked to satisfy. Now, before we move on to giving you the graph-based version of ABA, let me make some notes for those of you who maybe are familiar with other forms of structured argumentation, but not ABA. The assumptions in ABA are the divisible components. Okay, so they can be used to build semantically acceptable extensions unless there are reasons not to include them. And these reasons are what the different semantics dictate. So basically, assumptions are divisible bits of the language. They are the bits of the language that you're not sure about. You can assume or not assume, depending on the conditions that the semantics is asked to kind of satisfy. Assumptions are the only divisible components in ABA. So there is nothing else divisible. In particular, all the rules are strict. So they're all is taken into account. You can't choose which rule you apply or do not apply. They're all applicable. The only divisible component is assumptions. Attacks are only of the undercutting type, which basically means an argument disagrees only with the premises of arguments. They can never disagree with the conclusions of arguments. We can model disagreeing with the conclusions of arguments by massaging, by knowledge representation means, but not natively to ABA, only one type of attack is allowed, and that's the undercutting type. And also, we are restricting in this talk to flat, but there are interesting non-flat instances of ABA that we have considered. For example, several formalities for non-monotonic reasoning. Abstract argumentation and logic programming are instances of flat ABA and vice versa. Flat ABA can be seen as an instance of abstract argumentation logic programming when the sentences are atoms, are just atomic, okay? And that's a restriction. And bipolar argumentation is an instance of ABA, but non-flat ABA, but not vice versa. So there are non-flat ABA instances which cannot be mapped onto bipolar argumentation, even by restricting the language to atoms. Okay, so that's all I wanted to say about ABA. Let us now see why we need to do something different with ABA, why the conception of arguments as trees in ABA may lead to undesirable kind of rhetorical behavior, if you like, and why sets of arguments are also not the right conception, we believe. So let's consider a very simple example. This is a very simple ABA framework where the underlying language is sets of atoms, in particular P, Q, R, A, B, S, X are all atoms in the language L, which I'm not giving you here. I'm just hand-waving about it, but basically it's a set of atoms. And the inference roots are given here. So these are, the first rule says that you can conclude P if you have Q and R. The second rule says you can conclude P if you have B, etc. So there are basically two ways to prove P, two ways to prove Q, two ways to prove R. A and B are assumptions. They are the only two assumptions here. And they're contrary to some sentence X, which actually can't be proven here. So there is very little debate to take place. This is a very simple example to illustrate just the issue of arguments as trees and their problems. So this is a flat ABA framework because no assumption occurs in the conclusion of any of the rules. Assumptions only occur in the premises of the rules. Okay, so let's see what kind of arguments we can build from here. Here I'm giving you 4 arguments. Well, 4 proofs, kind of. The first one really is not an argument because it is not finite. So I'm just giving you to make the point that ABA arguments are necessarily finite. And it is something that can be considered. It's trying to prove P. It chooses the first rule, P, Q, R, to unfold, if you like, P, generating 2 further nodes, then it chooses the rule R if A here. Actually, I don't know whether you see my pointer. Do you see my pointer? Yes, okay, good. So R if A is chosen here, and here for proving Q, I have chosen this Q if P, which then, as you can see, introduces a circularity and a law. So this gives rise to an infinite tree, which we do not regard as an argument, we dismiss. The other three, instead, are proofs and they are legitimate arguments. The one here, the second one from the left, proves P by using the same rule that I used before, P if QR, and then once it comes to Q, it chooses the same rule as before, Q if P, but then makes a different choices, chooses P if B, which is the second rule for P here, okay? This argument is the same up until here, but then chooses Q if R, the second rule, and then R if B. And the last argument is very simple. It chooses the second rule for P, P if B, and that's it. So you can see that these are proofs. They are deductions, basically. The premises are all assumptions, and they are the leaves of these trees. And the nodes are all labeled by sentences in the language. And each node has as its children the sentences in the premises of an inference rule in the given set. Giuseppe has a question.
Yes, thanks, Francesca. One basic question. How do you know that at some point in the first argument, you won't choose B as a justification for P? Is there any notion which allows... Say it again, sorry.
In this one, in the leftmost one.
Yeah.
Yeah.
So can you make the distinction between, say, the second argument, where at the second step you have chosen a different reason for P, which makes the argument safe, right? And the first one, where you say indefinitely I will alternate P and Q, but how do you know that at some point B won't be chosen to?
Yeah, I mean, I don't know. Here I made the assumption that, I would keep on choosing the same rule for P. And computationally, this is very legitimate, because if you were to implement this in a naive backward chaining manner, when you actually choose a certain rule, you would probably still stick to choosing the same rule, because maybe you do it in order. So computationally, it's a legitimate choice, the fact that you will end up always choosing the same one. If you implement naively, of course, the construction of the arguments. But in general, you may have to introduce some kind of loop checking if you want. If you want to avoid that, you would have to introduce some kind of loop checking. And that's, also perfectly kind of legitimate. That, for example, realize, oh, here, I end up with the same P, loop checking, I need to choose a different rule. The point that I'm going to make is that these require somewhat some upfront computational machinery decision that would allow you to avoid undesirable, what we call undesirable patterns. But if instead of using trees, as we are doing here, you were to use graphs, you would not have this problem at all. So you would solve the problem of the infinite potential proofs that are no argument, but also you will solve other problems, because this is obviously a bad argument. It's not an argument in the first place. But the second and the third are also not good arguments. And indeed, the second one has a kind of circularity nonetheless. It's finite, but has a kind of circularity, because P is proven in terms of P itself. I mean, from a rhetorical viewpoint, I would call this a flawed argument. If you were to build an argument matching this logical structure in natural language, you would not be a rhetorically good arguer, because you would bring in the same point twice, so in a kind of nested manner. So this is something that I would argue, or we argue in the paper, is really not something you want. The third argument also is not good. It has a kind of redundancy. Why would you want to prove R in two different ways when it's the same thing? Why would you use B once and A another time? So this is also kind of rhetorically, mildly put, inefficient. You wouldn't really want to prove the same thing in two different ways. The third argument is the one really that is a good one. Is neither circular nor redundant. Yes, Marcello.
No, I wanted to ask you this also because probably you'll be more exposed to attacks if you prove it in different.
Absolutely, yeah. Absolutely. So you kind of rhetorically wouldn't do it. Why would you bring in B and A when you can just use B and you would be less prone to be attacked? Absolutely. So it's kind of inefficient. So I mean, these considerations are making them for ABBA, but I think any other structured argumentation framework that uses trees would have exactly the same problem. So we have not, in argumentation up until this work, been concerned with what arguments look like and whether it's really appropriate to define them as trees. Heikel, you have a question.
Yeah, thank you. Thank you, Francesca. Just, it's not a real question. It's just for me to help mapping the broader domain of argumentation into the field really of applicable AI. So this is why I'm asking. So just stressing this last point, I can just tell you, look, if you can support your P, Q, whatever it is, through two distinct paths, this is giving you a stronger argument, not a weaker one. So, I mean, how would you react to this?
Yes, it's true that if you have multiple ways to prove the same thing, that would, in a sense, allow you. So, if you've got a block path, to use another one, but in a sense, if you think about it, why would the third argument here, the one that uses A and B, give you a better path than the one just having B? Because you still have B, so that's still a problem for you. But you bring in A as well. So if it's problematic just to have B, it is still even more problematic to bring B and A. So I guess what you're referring to, and that's an interesting question, is also the problem of accrual, right? That if you have multiple ways to prove the same thing, then this gives you more strength. But are you really having multiple ways to prove the same thing here? Because you're using the same assumptions and more. So I would argue that actually this is, one thing is to say I can prove P using A or B. That's good. But if I can prove P using B or B and A, I don't think that's good. I don't think it should be accrued. So I can see where you're coming from, but I don't think that looking at building arguments with these redundancies strengthens anything from the viewpoint of applicability. At least that's my view.
Yeah, that's clear. Thank you.
Okay. That is actually more of a problem. I mean, at the moment I've told you arguments as trees are not ideal. They have these issues. But we can go further. We can look at sets of arguments and see that actually there are even more issues. Consider the same example as before. And now I'm considering two different extensions. One on the left, which includes two arguments, and one on the right, which includes two arguments. So as I told you, extensions are just sets of arguments satisfying desirable conditions. Let's ignore the desirable conditions for now. Suppose I put together these two arguments on the left, let's call this extension A, and these two arguments on the right, let's call this extension B. And they are legitimate sets of arguments. However, you can see that in one of them, we have that, in particular in the left, we have that R is proven differently in two different arguments. In one, R is proven using A, and in the other, R is proven using B. So this does not happen on the right, okay? So you could say that this is actually not a dialectically coherent position, because for the same reason that we said before for individual arguments, why would you want to have a debate where you bring in lots of opinions where you prove the same thing in different ways? And that's a kind of redundancies itself. And although this could happen when you've got a multi-party debate, if you've got a single lawyer, say, putting together a cohesive argument, meaning, a set of opinions put together, you would not have the lawyer been deemed to be good if it proves the same thing in two different ways in the context of establishing two different conclusions, P and S here. So this is a kind of redundancy again, okay? Which happens even if each individual argument is fine, is known has got no circularity or redundancy. So the redundancy may arise also across arguments within sets. Okay. The second one here is more, I would say, is dialectically coherent because you use A to prove R in all arguments. Okay. So this is really the motivation for us. The motivation is that we want to avoid circular arguments, which are basically arguments containing a directed path from a node labeled to some sentence to another node labeled by the same sentence. This was the second argument we saw a while back. You want to avoid flabby, what we call flabby arguments, which are non-circular, but they have different nodes labeled by the same sentences and whose children are different members of your language, extended language. So this is better than circular, but still has a redundancy. So we call this flabby. And we want to avoid bloated extensions where there are arguments that have nodes labeled by the same sentence, but with different children. Okay. So these are concepts of undesirable patterns for arguments and sets of arguments. Okay, so note that if an extension contains circular or flabby arguments, then necessarily it's bloated. So, but even avoiding circular or flabby arguments, as we saw before, you may still get a bloated extension. Okay, so these are again, I think these are concepts or argumentation, but to me they're concepts about deductions in general, really. Anytime you have deductions, you could apply these concepts. Okay, now there is another related concept that is important, and that's a concept of rule minimality. You can define an argument as being rule minimal if there are no two nodes labeled by the same sentence and the children are labeled by different elements, which basically means you use different rules for unfolding those nodes to obtain their children. And of course, a rule minimal argument is neither circular nor flabby. So if you prefer more conventional set theoretic notions, you could impose rule minimality instead. But sets of rule minimal arguments may be bloated still. So imposing rule minimality is not per se a recipe for avoiding bloatedness. Okay, now this is the motivation for what I'm going to define now. So basically, we could have said at this point, or even at the point before, well, let's just focus on ABBA and avoid circular flabby arguments and impose from the outside that we don't have bloated extensions. Instead, as I told you in the main motivation, we opted for a more organic solution, one whereby we change, if you like, the ontology underpinning ABBA, and we think in terms of graphs instead of arguments and sets of arguments. So our new ontological concept and our new conceptualization is based on replacing everything that ABBA had with arguments. We no longer talk about sets of trees, we talk about graphs. So let me define these graphs for you. So a graph, an argument graph, is a directed acyclic graph, which consists of vertices and edges, and we just use V of G for the vertices of G and E of G for the vertices of for the edges of G. And we have that the vertices are all sentences in the language, and for every sentence which is in the vertices, if the sentence is an assumption, then the sentence is kind of belongs to the sinks of the graph, which is basically the set of all vertices with no outgoing edges. So basically, you can't have edges coming out of assumptions. And the second condition is that sentences that are not assumptions are such that for each one of them, there is a rule in the set of inference rule in the other frameworks, such that there is an edge from a sentence to another, for the sentence S to another, if and only if the other is in the body, in the premises of that rule. So we use rules as before to unfold sentences. That's it. That's an argument graph. Okay, so we are simply imposing that there are no outgoing edges from assumptions, and that there are rules connecting vertices by means of edges. And in the specific case, when we have an argument graph, we talk about the support of the graph by looking at all the assumptions that are amongst the vertices of the graph. And we call an argument graph focused if it has a unique source, namely a vertex with no incoming edges. And that's the claim of that argument graph. I'm going to give you an example. It's even simpler than we had before. We have only three rules: P if B, R if A, and R if B. And we have two assumptions, A and B, with contraries X. This is the list of argument graphs you can obtain for this very simple example. Let's start from the beginning. You may say that A alone, the graph with one single vertex, A, and no edges, so an empty set of edges, is an argument graph. It satisfies the conditions are set to you. All the vertices are are sentences in the language L. Don't forget, A is a subset of L. And the assumptions are things, so there are no outgoing edges, and there are no non-assumptions, so we're good here. Similarly for B. For R, we can have an argument graph which links, with an edge from R to A, given by this rule here. Similarly for B. And then I can throw other stuff in. I could put B, and that's still an argument graph. It still satisfies the conditions we imposed. This shows that argument graphs do not need to be fully connected as trees, arguments as trees were. These first four argument graphs are focused because they've got a single claim, which is A here, B here, and R in these two. But this argument graph here is not focused because it has two claims, basically, R and B. So it has, in other words, it has two sources and does no claim. And so on and so forth. We can see that this is another argument graph where P and R are both connected by edges to B, because P if B, so this edge is given by this inference rule here, and this edge is given by this inference rule here. Okay, so these are just examples. And there is an important distinction with trees, arguments as trees, which is whereas arguments as trees have nodes of the trees labeled by sentences, argument graphs have nodes as sentences. There is no labeling. And so each node, each vertex, as I said, is a sentence. This means that we cannot have copies of sentences because each sentence stands for itself. So in this particular case here, B is a sentence that serves to support two different conclusions, but there is a single node with that sentence. Okay, so that's what the argument graphs are, they obviously represent the old style of arguments, tree-based arguments. Let's look at the original example that I've given you. So here we've got two rules. No, actually it's not the original, it's a bit smaller. and we only have one assumption A. So you can see here on the left an argument graph that I've constructed from here. And here on the right, these are all the tree-based arguments that are represented by this single argument graph. So we can look at some of the bits here. So P is here connected to Q and R. There are edges from P to QR because of the first rule. And then we go Q if S, so we have this edge, and we have R if SA, so here is these two edges, etc. So this is not a focused argument. It does not have a single source, so it is not a focused one. And it is supported by A. And here on the right, these are all tree-based arguments that are represented in a very compact manner. I guess you would agree with me on that, by this individual and single argument graph. So, for example, there is an argument for P where this inference rule, the only possible one for P, is used. Then for R, I go to S and A because of this third rule here. And then from Q, I go to S because of the only rule for Q. And then S goes to true, and S goes to true because S has, there is a single rule with an empty body. And A is an assumption, so I stop there. So this is what I would obtain if I were to construct a tree as an argument for P. And you can see that S is repeated because sentences here label nodes. And this is captured completely in here because I've got P if Q R, Q if S, R if S, S, and S is linked to nothing at all. So I stop there. Peter has a question.
Yeah, I have the following question. So that means that the head of a rule can never function as an argument, right?
Yes, actually, yes, even though if I were to build a graph-based argument for S alone, I would have that the single head of a rule would function also as an argument, but that would be an accident. So ontologically, you're right. There is a big distinction between sentences and arguments. Arguments are made up of sentences. So the head of a rule is a sentence. Yes.
So how do you compose arguments? So if I have an argument from an assumption, I mean, if I want to compose it with something that I have already proved, this should not be possible then on your ontology.
We don't have the concept of composition, but we have the concept of sub-argument, which maybe is what you're referring to. Yeah. So here, for example, I have an argument for A alone, which is just assuming A. And I have an argument for S alone, which is basically saying S is a fact. So, it has an empty body. So I've got these two arguments, which are sub-arguments of this larger argument here. So I have a sort of composition because arguments are made of sub-arguments as well.
But the sub-argument is not an argument, right?
Yes, it is on its own. So here, if I look at it outside, this is an argument on its own, but I don't need to give it explicitly. I can give it as part of this single. Yeah. So I could just say this is the only argument I have. Yeah.
Yeah. Okay. Thank you.
But we could actually define deductions in a way, and I think some approaches I think probably Aspect does that. You could kind of define arguments as compositionally made of sub-arguments. So you have you put together arguments so that they are connected by what you need as premises in one and what you can prove as conclusions in another. It just, we don't do it in ABBA, but conceptually, I think that's what implicitly we are doing.
Yeah. Okay, thanks.
Okay, Atefe, you have a question.
Toni, could you return back to the previous example?
Yeah.
Here you didn't present a R with two children, A and B.
R with two children, A and B. Yes, very good question, thanks. So indeed, what we impose is that there is a single rule that links a sentence with the body of a rule. So here, it would be wrong to connect to B because I would use a different rule. Okay, so if you look at the definition, there is a single rule. I should have said single. So there is a rule, no more than one. So that's why I don't have this there.
Thanks.
Okay. Any other questions at this point? Okay. So argument graphs compactly represent tree-based arguments, and also sets of arguments can be converted into argument graphs. So you can go back and forth. So we define what we call the graphical conversion of an argument, A in this case. So let A be a tree-based argument. So a focused argument graph is a graphical conversion of that tree-based argument if they have the same claim, and if an edge belongs to the edges of the argument graph, then there are nodes which are labeled by those sentences, basically. So we can map tree-based into a graph that way, and we can also consider sets of tree-based arguments and convert them analogously, basically. Just we consider everything together. So there is a mapping between thinking of arguments as trees and sets of trees, and thinking of arguments as graphs and not having sets, just having graphs. Okay, so this is just an illustration that goes from sets of arguments to argument graphs. Suppose I've got these two arguments here, which are obtained using the sets of inference rule up here. So R if P, for example, is given by this inference rule. Then on the right, I show two graphical conversions for these sets of arguments. And you can see that again, it's much more compact. So I'm basically defining these as such that everything that occurs in here, all the edges are somewhat encountered in the trees. So here I've got a connection between P and R, because, and I find it here, one between R and B, and I find it here, and one between P and B, and I find it here. But you can see that I don't include lots of things that are in the trees, because the definition of argument graph does not allow me. It doesn't allow me to have that P would have both A and B as a child, because P is not labeling nodes. P is a vertex, so there is only one thing that can come out of it. Okay, and this is another one I can obtain. So you can take arguments as trees and sets of arguments as trees and obtain very compact argument graphs. Okay, so some properties of these argument graphs and of tree-based arguments as well. So no tree-based argument represented by an argument graph may be circular or flabby. So we avoid undesirable effects. So once you do the transition we did before, we lose. And here, note, this one was flabby because P is having two different children at different points. So in the translation, we lost this flabbiness. Okay, so we gained the properties we are after. Non-circular and non-flabby arguments admit a unique conversion as argument graphs. Non-bloated sets of arguments admit a unique conversion as argument graphs. Every focused argument graph is such that it admits an argument as a tree with the same claim and support. And for every argument, there exists a focused argument graph with the same claim, but possibly smaller support, as we saw in the example before. Also, the set of arguments represented by an argument graph is never bloated. So by changing conceptualization from trees and sets of trees to graphs, we immediately gained all the desirable properties we're after, namely non-circularity, non-flabbiness, and non-bloatedness for free. So we automatically get it. Okay, so this is overall, I mean, the big part of my talk is over here, but I want to tell you a little bit about what we do semantically with this, with these new types of arguments. So given two argument graphs, we can define attack. Atefe, sorry, you have a question still, or is it the old question?
No, I do not have, sorry.
Okay, sorry. You still have got your hand up. So, we basically say that, as we said before, attacks are driven by proving the contrary of assumption. So given two argument graphs, one attacks another. If there is an argument, if there is an assumption in the vertices of the attacked graph, such that some sentence in the attacking argument is its contrary. So attack is still driven by contrary, but now it's about sentences that occur in the graph rather than necessarily claims of arguments or supports of arguments as we had before. And this is a very simple example. I've got P if A, P if B, X if Y, Y if C. A, B, and C are assumptions. The contrary of A is Y, the contrary of B is Z, and the contrary of C is Y as well. So I can build an argument graph with claim P, and A is the support, and this is attacked by this argument here, because this argument here proves the contrary of A, which is Y. And going back to Peter's question now, you can see that the sub-argument for Y counts, because you can really use the sub-argument that concludes Y within this graph as a reason for attacking this other argument. So we get serendipitously this concept of subgraph or composition. This argument attacks itself too, because it is supported by C, and it proves Y, which is the contrary of C. Okay, so you can define naturally attacks as you were defined, as for ABBA, no difference here, and this is just an illustration. Okay, now, once it comes to the semantics, I need to give you some, some preliminary notions. How much time have I got still? Sorry, I realize that it's 10 to 1 already.
Francesca, there are 10 minutes left, then it depends on how much room we want to leave for questions.
Okay, so maybe I'll just very, spend 2 minutes on giving you a flavor of what the semantics are. But what I want to tell you, I already told you, so we can go quickly. Basically, we define what we call rule consistency, which is maybe not the best name with hindsight, but basically it's about saying you have a rule, a set of rules, of inference rules is rule consistent if there are no two rules in it which prove the same conclusion. Okay, and then you can define maximal rule consistency using subset maximality. I don't need to give you an example of this. So now, given also you can extract rules from argument graphs, because you just look at the rules that have been used to generate the graph. Now, given a maximally rule consistent set of rules, considering the set of all argument graphs that can be built from those rules, we can define the characteristic function with respect to the set of rules, which is basically looking at defense. It's looking at when it's applied to an argument graph, it kind of computes all argument graphs which are defended by that graph by attacking all attacks against those, that argument. This is the same as what happens in doing subset argumentation, in standard ABBA, but it's with respect to this conceptualization of argument graphs. And then you can use, we have proven that this characteristic function has a least fixed point that, applied starting from the empty graph that we represent with this diamond, and then define the semantics using this characteristic function. Conflict freeness is just non-self-attack, and then admissibility is defined in terms of a graph being the subset of its characteristic function applied to it. Completeness is equality with the characteristic function. Groundedness is minimality. So basically, we can redefine semantics, and we focus only on these semantics: admissibility, completeness, and groundedness, using this kind of characteristic function. And we prove results which are about linking this new conception of semantics and the old conception. So if you take an argument graph, and then you take the set of tree-based arguments which are represented by the graph, then you can basically prove that if the original graph is admissible, then the set of arguments represented by the graph is also admissible in the old ABA sense. And similarly, we have connections between the various semantics. I don't have time to go into details. I just wanted to conclude, so maybe we have 5 minutes for questions. Structured argumentation is best understood in terms of graphs. That's the point of this work. I have not talked to you about lots of things. The semantics I've done very quickly, but also I've omitted the computation, and we have an implementation for a computational machinery for these graphs that is available here at this link. And we prove that computationally it is advantageous to use graphs. So there are not only conceptual advantages from a kind of a rhetorical viewpoint, if you like, there are also computational advantages. And I'll stop here. Thanks for your questions so far already and for your attention.
Okay, thank you very much, Francesca, for the very interesting and clear talk, at least up to the last few slides. Because of course, you had to go in a hurry, so it was a bit difficult to follow. Yeah. But thank you very much. By the way, before turning to questions, I just realized I forgot to mention that Francesca has been recently awarded an ERC Advanced Grant on argumentation-based deep interactive explanations. And so this is just, it's a piece of information that I forgot to give you.
Thank you. That's.
Right. We have time for